I'm Svetlana von Gratovsky from Institute of Radio Engineering Electronics, Moscow, Russian Academy of Science, and I will be chair of this Google meeting. So today we are so happy to make a presentation of Professor RANA BISWAS. Professor RANA BISWAS he did his Master Science in Physics in Indian Institute of Technology, Mumbai, and his PhD in Condensed Matter Physics from Cornell University in Ithaca, New York, in 1984. He's a postdoctoral member of staff at IT and T Bell Laboratory, Murray Hill, New York, and a consultant with Exxon Research, RANA label, New York. He then moved to Iowa State University and Ames Laboratory, where he is an adjunct professor with the Department of Physics and Electrical and Computer Engineering, and the Senior Science in Army Laboratories of U.S. Department of Energy and Microelectronics Research Center. His research has spanned solar material, nanoplasmonic, nanophotonics, quantum materials, and nuclear magnetic resonance of materials. He has co-organized several symposiums at Spring Material Research Society meeting and co-edited preceding volumes. He has supervised PhD students for their thesis research and postdoctoral scholar for Iowa State University. His publication in Nature and other high-impact journals have been cited extensively and resulted in a high index of 55. He directed several projects from National Science Foundation, EPRI, Department of Energy, and industrial sponsors, Tritons, ECX Photonics, Ageltron, and have been also consultant with Xerox. He is fellow of American Physical Society, a senior member of III, and a member of MRS and SPIE and ECS. So please start. We are waiting for your presentation.
Yeah, thank you for the very nice opportunity to present at this virtual conference. Very nice variety of subjects are being presented. So this work was done at Iowa State University, supported by National Science Foundation, Department of Energy. And I used the NERSC Supercomputing Center resources. And a lot of this work has been done by Akshit Pier, who did his PhD here, one of our most excellent students at the university. So just a small geography. So we are located in the state of Iowa. It is here in the upper Midwest, south of Minnesota, and it is west of Chicago. So it's in the northern region. You look at the map of Iowa over here. We are in this city of Ames. So that's where the university campus is located. It's a short distance from the capital city of Des Moines, which is the airport. And the other university here is University of Iowa, located in Iowa City. So that's about 140 miles from here, east. I want to also mention that I am part of Ames National Laboratory. This is a Department of Energy National Laboratory, part of the 17 national labs operated by the Department of Energy. And we are over here. This is an Office of Science laboratory, and we do applied material science and engineering, chemical and molecular science, condensed matter physics, with a big emphasis on nanomaterials. And you can see that this lab has 473 employees, some part-time, some full-time. And my role, I'm part of the solid state NMR Center. We do very high field nuclear magnetic resonance and study nanomaterials and 2D materials. So the Ames lab is a campus within a campus. And I will not be talking about the work I do with the Ames lab. I'll be talking about the work with the Iowa State University programs. But just to give you an introduction, now we all work on nanostructured materials, and periodic systems are well known in nature to provide strong optical diffraction, such as the butterfly wings. You can see here, this is what gives the color of the butterflies through diffraction. Then we have the opals, which occur naturally in nature. And the opals are actually a photonic crystal, which manipulate light through diffractive effects. And in all these systems, we have either periodic dielectrics or metals, and we can use them to enhance optoelectronic devices. Now, at the same time, we can engineer these nanomaterials and photonic crystals. And one area which we worked on is also biological systems, because periodic surfaces, such as the ones you're looking at here, have much larger surface area. And these are key attributes for hydrophobicity, cell growth, and drug delivery. So what we are going to do today is focus on novel light matter interactions in nanostructured and quantum materials. And as you will see, this has some implications for quantum information science as well. So I want to take you back to one of the important discoveries in this field of nano-optics. And this was the discovery of sub-wavelength Hall arrays. And the phenomena was extraordinary optical transmission, EOT, first discovered by Ebbison and his group in 1998. So what you have here in these systems, you can see on the lower two figures, is a sub-wavelength array of holes etched in a metal film. And the principal observation is that you have a transmission peak, which occurs at a wavelength very close to the pitch A of the structure. So that's the T00. And in addition, you have a second peak, the substrate peak, which occurs at a wavelength refractive index of the substrate times the pitch. So you can see that's quite a sharp, large peak over here. For both of these, the transmission is enhanced dramatically over the expected classical value for this area of holes. And the holes are quite small, less than 0.29 times the pitch, so no waveguide modes can propagate through the structure. So this has been a very fertile platform for nano-optics that's been used in many different laboratories. So just the basic mechanism of this, it's now quite well known that the instant light comes in, it excites the surface plasmons at the front surface, and it creates evanescent field within the aperture. So this evanescent field excites the surface plasmons now at the back surface. So you have two surface plasmons generated at both interfaces. They couple strongly, and light tunnels through this Hall array. The momentum conservation of the parallel component of the wave vector tells you that the surface plasmon wave vector is the incident wave vector, parallel component, plus the reciprocal lattice vector of this periodic structure. And this can be solved quite readily, and it gives you the dispersion relation for surface plasmons, which actually lies slightly below the light line. And you can see that the wavelength of the surface plasmon uh, is a function of the different orders of diffraction. And in the lowest order, it is very close to A. And here, epsilon 1 is the dielectric, and epsilon 2 is the dielectric function of the metal, both of which are wavelength dependent. So this phenomenon leads to very high field enhancement, more than a factor of 100 within the holes. And in fact, here is a calculation that I have done for the whole array. You can see the field is very high at the boundaries of this hole. And this is for field polarized in the x direction. And this very high field has led to enhanced sensors of various types. And for many years, I worked with this company, ICX Photonics, and we developed high sensitivity gas sensors using the infrared properties of these whole arrays. So the first thing you want to note here is that to make a whole array is a very complex fabrication process. And in the early days, most people used e-beam lithography for the patterning. And this resulted in very small whole arrays, less than 1 square millimeter. So obviously, you need very advanced microelectronics facilities. And then to make these optical measurements, you require a micro spectrophotometer to measure optical properties of very small area structures. And this approach is then not suited for applications where you need very large area samples, like solar cells, and organic light emitting diodes, and even most optoelectronics. So what this motivated us is to develop a simple alternative to this fabrication process. And here we use replica molding. And this was actually really the work of Akshit Peer, who did an excellent PhD here. He actually published 10 papers during his PhD years here. He joined Intel, and he's now in the basic research side of Intel. So what we start with, we have these, we can start with a glass, and then we spin coat polystyrene film on it. And now we have a PDMS patterned mold. And we'll come back to that later. We usually replicate these molds from a master pattern in polycarbonate. And we've had a very long-standing collaboration with this company, Microcontinuum in Massachusetts, that provides these master patterns to us. And then we imprint it on the PDMS mold. So then we use the PDMS mold to imprint the polystyrene film. And there are various conditions, high temperature and pressure, as you can see here, that help you to replicate the pattern, the inverse of the pattern. So once we do that, we sputter deposit gold on this array of nano cups here on the polystyrene film. Now, this is results in samples you can see that are more than 1 centimeter across. So it's very convenient to do measurements on such large area samples using just normal spectrometers. Now, the gold deposition is a little bit different from what most people do. So, what we do is we do the deposition at 45 degrees, and we also rotate the sample. And this results in a coating both on the top and on the side walls. But if you look more closely, the gold coating is non-uniform over this array. So it's quite thick at the top, about 100 nanometers, but considerably thinner at the bottom. We estimate it's ultra thin, just about 5 or 10 nanometers at the bottom of this nano cup over here. And this thickness is considerably less than the skin depth of gold, which is 25 or 30 nanometers at optical wavelength. So what we have done, we have made a continuous gold film without any etching. And you can see the results for the different polystyrene concentrations in solution. So as you increase the polystyrene concentration from 2 to 10%, the depth of the nanocups decreases. The pitch, of course, stays the same with 750 nanometers, and the radius is about 250 nanometers. So the pattern is best defined for the low concentration of polystyrene. So the next thing we did is we went to the spectrometer and we measured optical transmission. And here, the first thing you see in all of these three films is the surface plasmon resonance peak for gold, which is well known to sit at 504 nanometers. And that's when the scattering cross-section of light goes to 0. So, and that doesn't change in wavelength, of course. The second feature is lambda 1, this extraordinary transmission peak. And it occurs at about 700 nanometers in all these three samples. So it's very close to the pitch of this structure. And the last feature is lambda 2, occurring at about 1000 nanometers, particularly for the first two films. And this is the refractive index of glass times the pitch. It's very close to that. So in summary, we are seeing this extraordinary optical transmission, even though we have a continuous metal film. And we did no etching. So this was our big finding when we did these experiments. So then we set out to understand what is actually happening by doing simulations. And here we do scattering matrix simulations, calculating the transmission of light through this nano cup in a gold coated substrate. And what you see here, if you sit at the resonance, 700 nanometers, there's a very high field that is localized within the nanocup. And this field penetrates through the bottom of the nanocup over here into the glass substrate. And it does that because there's an ultra-thin gold layer, which is much thinner than the skin depth. And it gives you this narrow cylindrical profile of the transmission into the substrate. So this is what leads to the extraordinary optical transmission peak in this continuous gold film. And if you look carefully at the scales of this, you will see that the transmission, the electric field intensity is more than a factor of 100, close to the bottom of the holes. And over here, I plot the simulated transmission, the total transmission in red, and the specular transmission blue. And it compares actually quite well with the experimentally measured transmission. So that's the experiment. And we are sitting at the resonance over here, lambda 1. And the other feature on the right is the surface plasmon of gold. And here the fields are concentrated more at the surface, you see, and not at the bottom of the gold film. So the behavior is, of course, quite different. Now, if you change the periodicity of the nanocups, you'll see that the wavelength of the transmission peak scale with the pitch quite readily. And if you make the radius of the cups larger, then the peak of the transmission become broader. And these are all well-known effects. I show the simulation results, but other authors have verified this experimentally as well. So it's good to operate in this region of a little bit narrower radius. And this has been a very good platform for biosensing. And here the idea is that you can coat these films, or you can absorb a protein layer, and usually such biolayers, biomolecules, have a little bit lower refractive index of 1.4. And when you do that, even for small thicknesses, 5 to 15 nanometers, you will see a redshift of the transmission peak that you see here on the red. And this shift depends linearly on the coating thickness. So many other investigators have used this property to detect biomolecules and proteins on this structure. And they are all the time making use of this very high optical field inside the structure. And this is where you want to have large area structures, and you can make large pixels for biosensing, and you can readily measure the transmission spectra to obtain the film thickness. So while I was presenting such results at conferences, I was contacted by the group at Los Alamos National Lab, which is one of the experts in fabricating quantum dots. And the basic idea in this figure you can see is that if you put a quantum dot inside the structure, and the quantum dot sits in a solution environment, you can tune the photoluminescence decay wavelength exactly with the transmission wavelength of this whole array. So you see this is in red, the photoluminescence of the quantum dot. And our collaborators used these copper indium sulfide, zinc sulfide quantum dots in solution, which sit exactly to have a maximum of 700 nanometers in their photoluminescence. So the hypothesis is then the photoluminescence decay of the quantum dots is enhanced by the intense electric field at the bottom of the nanocups, and it should make this decay much faster. So this opens up new possibilities for light-matter interactions, combining nanostructures with quantum materials. So to show you the way this was done experimentally, you had these copper indium sulfide quantum dots in solution coated on nanocup structures, and the photoluminescence decay was measured using a wide field optical microscope using a short wavelength 403 nanometer pulse laser excitation. Now, we fabricated 3 different samples with these quantum dots. So the control sample, the quantum dots were spin coated on flat glass. That's one. The second sample, you have a flat gold film, and then you spin coat the quantum dots. And the gold film has the same transmission as the nanocap array at this resonant wavelength. And the third one is the nanocup array that I show you. And here, when you spin coat, the quantum dots go inside the nanocups. So these are the first measurements of the photoluminescence decay as a function of time for the glass in blue, the gold film in green, and the nanocup array in red. And you can immediately see that the decay rate is much faster in the nanocup array. And in this field, it is usual to fit these decays by 4 exponentials. Uh, and the details are just listed over here. And you see the average decay time in glass 200 nanometers, gold film 112 nanoseconds. Sorry, nanocup, it's about 46 nanoseconds. So the average decay time for quantum dots is faster by a factor of more than 4 when you compare nanocups with the glass. And there's a slight quenching for the gold film as well. So it's a very marked effect, and you can see that in all of these exponentials. The nanocup is always the shorter time, and it's in fact quite a bit shorter. So uh, it's of interest to look at the wavelength dependence of the photoluminescence. So you can either sit out of resonance. So when you're at band 1 or band 2, you are outside the resonance peak. So that's the blue or the green bar here. And you see then the glass and the nanocup are more or less having the same average decay time. But when you go in resonance, band 3 or band 4, around 700 nanometers, that's when you see this marked difference in the decay times of the nanocup. So this is what makes a difference in the resonant behavior. And these measurements were done by using an angle tunable bandpass filter, and you block selectively these different wavelengths. And you see this same effect as a function of the time delay. So when you're off resonance, 660, 625 nanometers, then you see the glass and the nanocup more or less are the same. But when you're on resonance, then you see this much faster decay of the nanocups than on the glass film. So we established this very well experimentally, and then we simulated this effect by using finite difference time domain simulations by placing a classical dipole to model the quantum dot, and the dipole emits in X, Y, and Z polarizations, and the dipole can be placed at different positions within the nanocup. So it's typical in this field to obtain the Purcell factor, which is the ratio of the dipole power within the resonator to the dipole power in vacuum. So this is telling you how much the field is enhanced and inside this nanocup, and how that is affecting the radiation power of the dipole. So if you're very close to the bottom and you're looking at this region for small d, you want to average the X, Y, and the Z polarizations, and you get an average Purcell factor that's very high, you see 86 or so. But realistically, you have to look at all these different positions of the quantum dot or dipole, So once it sits quite a bit above the bottom of the cup, then the Purcell factor, of course, goes down. And when you average over the entire nanocup volume, the Purcell factor can be much lower, as in the experiment, and approaching the factor of 4. So it's highest when the dipole is close to the nanocup bottom, but quite a bit lower when you go further out. And you're just sitting further away from the field maximum here. So let me then move to the next part of this talk, which is now, we did the same type of experiments with these nano arrays, and we found a very interesting phenomena, the presence of surface tribocharge. So what I showed you in the previous part, we started with a template of polycarbonate, and this is a nanocone array in gray, and we had this PDMS layer on it, and we peel it off after curing. So that's how we got the nano cups that I showed you in all the previous experiments. So you first, of course, look at the AFM, atomic force microscopy results. And if you traverse over this blue line over here, you see the trace of these nanocups. So it's about a depth of 160 nanometers, as you expect. So this is the flat portion, and this is the bottom of the nanocup. So there's no surprise there. But at the same time, we have the surface Kelvin probe microscopy set up, integrated with the AFM. So that's SKPM. SKPM. So this measures the surface electric potential during the same scan. So that's the red line. And then the very surprising effect that we found is that the surface potential varies by several volts. You see, 5 volts from the top, the flat portion, to the bottom of the nanocup. And not only does it go through a minimum, but there's also a secondary maximum at the bottom of the nanocup. So it was a very unusual effect that we saw, and we, of course, repeated this on many types of samples, nanocups and later with nanocones, and we confirmed that the surface potential varies rapidly. And the only way this can happen is that the nanocups here have negative charge that you can see schematically over here. And this is caused by the frictional stress during the demolding or peel-off process. So these results were published in Nature Communications in 2018. And to understand them more carefully, together with my collaborator, Professor J. Kim, we did electrostatic modeling. And here, the idea is you put charge on the surface of this nanocup. And in white is the trace of the AFM tip as you scan across the surface. Now, if you have uniform negative charge, then you get the trace over here, which is the black line. So sure, it shows a deep minimum in the nanocup, but it is unlike the experimental data, which is the dotted line, which are shown by the dots here. However, if you put the charge in a smaller region, right at the rim of the nanocup. So it sort of forms an annular ring-shaped structure. Then you get the surface potential in red. So you see it tracks very nicely with the experimental measure. So you see you have about 50 nanometer wide ring and the surface charge density of about 9 millicoulombs per square meter. And it's less than 1 elementary charge per 10 nanometer square. So these are very strongly charged structures that result from the frictional stress in the nanocup during the demolding. And I don't want to elaborate on many of these details here, but this was highlighted in Physics Today that year. And what we did, we took that PDMS charged nanocup array and we used the PDMS to transfer the pattern into a photopolymer. And here you're looking at the photopolymer, which also had a secondary pattern, these stripes that were created by laser interference spectroscopy. And the secondary pattern had a pitch of 2.5 micron, whereas these nanocups had the same pitch, 750 nanometer. But this results, as you can see in these nanocones, which we call nanovolcanoes. Now, there's a small depression here at the top of the cone, which we call the volcano. And this depression is the indication of the charged ring that resides around the rim of the nanocup. And it is the charge of the ring that gets transferred into the photopolymer. So this is another indirect evidence of the presence of very strong charge in these nanostructures. So let me then move to the third part of the talk, how we can use these nanostructures in optics. And I know, this is a conference on Raman spectroscopy, and most of you are engaged in different types of optical phenomena. And here, the phenomena that we studied in the last several years is organic light emitting diodes. You have a high index organic layer, and you have an emissive zone, that's the one in red over here, and you have light being emitted from that layer. Now, the problem in this device, it is actually very well known, is that if you look at the emission sphere, there's an air cone, and which is the stop area. Then the light can only escape to the air side through this air cone, and this has a fractional area of 1/2 n squared. So this is only about 20%, unfortunately. Most of the light is trapped in substrate modes, which is about 20%, 25% or so, and a large fraction trapped in these waveguide modes in the high index organic layer. So the problem is to get the light out of the structure and to not have these waveguiding modes trapped within. And in addition to the optical losses, there are also plasmonic losses of about 20%. And those do depend on the position of the dipole and its separation from the cathode. So more detailed simulations show you that it depends on the ETL thickness, but in all cases, you can hardly get more than 20% of light out of the structure. So the basic idea is to uh, provide strong diffraction and diffract the substrate modes and the waveguide modes back into the air core. So that is done by using the reciprocal lattice vector of the periodic array, and it brings these waveguide modes back into the air cone, which then can be emitted into the air. So the structure that we developed experimentally is very much like the one you're looking at here on the right. You have a glass, uh, it's actually a polycarbonate structure, and you saw the template of nanocones on that structure in the previous view graph. And on that, we spin coat the organic layer so that grows in a conformal pattern. And you have the HTL and then the ETL. And the boundary of that is the emissive layer, which I'm kind of showing you in this red over here. And then on the top, you have the silver cathode, and that also becomes a conformal structure. So these are the cones. So it's a very highly corrugated structure, and the emissive dipoles, uh, like that nano cup, they sit in different positions. So they can sit at the top of the nanocone, or they can sit more towards the polycarbonate substrate. So there are different positions, and there are also different polarizations. So the sum result is that one wants to average over all the polarizations and average over most of the important positions. And what you're seeing here is the result of simulations which were just published last year. And it shows you that the outcoupling of light can reach 60% for either red, green, or blue if you have an optimal pitch of about 1 to 2 microns. And the remainder of the light goes into these wave-guided modes or substrate modes, and a small amount of light is trapped in the plasmonic modes, less than 10%, much less than a flat structure. Now, of course, if you have a large pitch, then it goes to the limit of a flat structure. And then you see the problem, you're back to about this 20% outcoupling, low outcoupling, and most of the light trapped in these wave-guided modes. Fortunately, this phenomena is not sensitive to the height, as long as the height is more than generally about 100 nanometers or so. So this is a great boon for the fabrication. And we have some experimental results which have just been published just about a week ago, which concentrate more on this region in the middle that demonstrate outcoupling of the order of about 50% experimentally. So this is a very encouraging experimental result, and we hope to actually do even better with the experiment that would bring it closer to the theoretical prediction. So I think this might be a good time to conclude. And in the first part of the talk, I showed you extraordinary optical transmission achieved with nanocap arrays fabricated with a very simple, low-cost, scalable method. We used a continuous gold film There was no lithography or etching, but the gold film had varying thickness, and this enables spatial regions of high extraordinary transmission through the ultra-thin region of the film. We then put the quantum dots within this nanostructure, and this quantum dot coupled to the enhanced electric field to produce a fast decay rate. And this was measured with time resolved luminescence and simulated with these optical simulations. Then in the next part, I showed you the formation of very strong tribal charge on these nanoarrays. And that is the effect of the frictional demolding during the replication process. And these nanoarrays are a platform for active photonic structures to enhance organic light emitting diodes. And I'm sure that these would have more applications to quantum information as well. So a lot of the early work was done by Akshit Pierre, and Yu Zhang was another student here. He's still continuing here. And the group at Los Alamos National Lab worked on the quantum dots and the photoluminescence measurements. Very, very well-known group there. And I want to thank my colleagues Jay Kim and Professor Cho at Iowa State for the work on the tribocharge, and Professors Ruth Shinar, Joseph Shinar for the organic light emitting diodes. And none of this work would have been possible without our collaborations with Microcontinuum in Massachusetts, and our longtime collaborator was Dennis Slaper, who provided these nanostructures to us over large areas on their roll-to-roll facility. Okay, so I can close now, and I'm happy to answer questions. Thank you. Thank you.